Welcome to Part 3 of Chapter 4, Chemical Bonds. During Part 1, we discussed ionic bonds, and during Part 2, we discussed polyatomic ions and some naming conventions. During Part 3, we will be discussing covalent bonds. In many cases, elements will react by sharing electrons instead of gaining or losing electrons. When this occurs, it's called a covalent bond. Two atoms share a pair of electrons to form a covalent bond. Atoms can form multiple bonds with each other by sharing 1, 2, or 3 pairs of electrons. These are called single bonds, double bonds, and triple bonds. The naming schematic for covalent compounds is a little bit different than ionic compounds. We begin by using a prefix to designate how many of a specific atom are present in a molecule. For example, mono represents 1 atom, di represents 2 atoms, tri would represent 3 atoms, etc. Binary covalent compounds have 2 names. The first name comes from the prefix and the name of the first element. In the case where there's only 1 atom of the first element, the prefix mono is dropped. Then the second name is going to come from the name of the second element. A prefix and a suffix are added for the name of the second element. The suffix in this case will be IDE. Let's look at a couple of examples. First we have SBr4. This is sulfur tetrabromide. The first name, S, comes from sulfur. There is no prefix in this case because we have only 1 sulfur atom. The second name, tetrabromide, comes from the second element. In this case, we use a prefix of tetra because there are 4 bromides, and we use the suffix "ide" because it's the second element in the compound. The next example we have is P2O3. In this case, we use diphosphorus as our first name because we have 2 phosphorus atoms, so we add the prefix di. There are 3 oxygen atoms, so we're going to use the prefix tri for the oxygen, and then we use the suffix IDE as it's the second element in the compound. So it becomes diphosphorus trioxide. The next concept that we will look at is a concept called electronegativity. Electronegativity is a measure of an atom's attraction for the electrons in a bond. For example, imagine if we had a carbon and hydrogen bonded together. These electrons are being shared between the carbon and hydrogen. They are floating between the two. We can almost think of this bond as a tug-of-war match between the carbon and the hydrogen. And electronegativity is a measure of how strong one of them is relative to the other. Carbon has a higher electronegativity than hydrogen. So the electrons, the 2 electrons that exist in this bond between the two, will be closer to the carbon. It's winning this tug-of-war match. The trend for electronegativity is that as we go towards the right of the periodic table, it'll become higher. This is because the atoms towards the right of the periodic table only need 1 electron or 2 electrons to obtain their noble gas state. So they end up with a higher electronegativity or attraction for the electrons in a bond. This leads to the concept of a polar covalent bond. When there are 2 atoms with different electronegativities forming a bond, the electrons are drawn closer to the atom with the higher electronegativity. This creates a small separation in charge. Because the chlorine has more electronegativity, it pulls the electrons closer towards it, it has a partially negative charge. And now the hydrogen, which is losing the tug-of-war match, has its electrons pulled away from it, and it develops a partially positive charge. This charge separation leads to a polar covalent bond. The electronegativity difference between 2 bonded atoms can help us to determine what type of bond is formed. If the electronegativity difference is low, This is a nonpolar covalent bond. These two atoms are sharing the electrons pretty evenly. A polarity electronegativity difference between 0.5 and 2.0 leads to a polar covalent bond. In this case, one of the atoms is hogging a large amount of the electron density of the bond. But it's not so high that the electrons are completely stripped from the other atom. As a rule of thumb, any electronegativity difference that's greater than 2.0 leads to an ionic bond. In this case, the more electronegative atom is completely removing the electrons from the less electronegative atom. Up until this point, all of the examples that we've looked at are atoms or elements that are moving two electrons back and forth. There are some cases where an atom or molecule will have an unpaired electron. This atom is known as a free radical. There are a few examples of free radicals, including nitrogen monoxide, nitrogen dioxide, and bleach. These molecules will have unique reactivity and are often associated with carcinogenic molecules and risks of cancer. Once we learn information about the number of bonds an atom is making and the number of electron pairs on the central atom in a molecule, we can gain some information about the shapes of molecules. This is called VSEPR theory, or valence shell electron pair repulsion theory. Electron pairs have negative charges, and therefore they want to repel each other. And so this causes specific structures to occur within the molecules. Here are an example of some common structures within molecules. We could have a linear molecule, a bent molecule, a triangular molecule, a pyramidal molecule, and a tetrahedral molecule. This chart, table 4.6, is used to help describe what type of molecular shape a molecule will have. For example, if a molecule has two bonded atoms with 0 lone pairs, then that will be a linear molecule. If a compound has 3 bonded atoms with 0 lone pairs, then it will be a triangular molecule. Molecules will have different properties as either polar or nonpolar molecules. In order for a molecule to be polar, two conditions must be met. First, it must have polar bonds. We looked at these when we were talking about electronegativity. Secondly, the polar bonds must be arranged in such a way that a separation of charge exists. The bonds can't cancel each other out. Here's an example where we have a separation of charge occurring. In this tetrahedral molecule, all of the different separation of charges are pointing in opposite directions. This leads this molecule to be nonpolar. In this molecule, ammonia, we have 3 polar bonds, and they're all pointing in the same direction. These bonds don't cancel each other out, and what we end up with is the top of the molecule being slightly negative and the bottom of the molecule being slightly positive. In water, this occurs as well. Water is an oxygen bonded to 2 hydrogens with 2 lone pairs as well. This creates a moment of polarity, or a dipole moment, in the direction of the oxygen, which leaves a negative charge on the oxygen and a positive charge on the 2 hydrogens.